Section 2.6 looks at logical equivalence. So we're going to say that two statements are logically equivalent if they have the same truth value for every possible combination of inputs. Sorry, I wrote outputs here. Let's fix that. So, for example, I can say that P if and only if Q is logically equivalent to P and Q, or not P and not Q. So let's actually see that. I want to show that they have those same truth values. So I'll take my P and my Q. Just like we did in section 2.5, we'll draw out all of the possible inputs for P and Q, following the pattern we like to use. And then we have P if and only if Q. And I'm going to build up this other one a little bit slowly, so I'll start with a P and Q. Then I'll also look at a not P and not Q. And finally, we'll put those two together to get P and Q, or not P and not Q. Okay, so we've seen for P if and only if Q, the truth table has a true if they're both true or they're both false. Right, these statements have to be either true at the same time or false at the same time. If one is true and the other is not, then I get a false. Now we can go through and build up our other one. So P and Q should only be true if both P and Q are true. It'll be false everywhere else. Not P and not Q is only true if not P and not Q is true, which is only true if both P is false and Q is false. So down here, where P and Q are both false, not P and not Q are both true. So I get not P and not Q. Otherwise, I get false. And now, finally, I'm taking the or of these two entries. So true or false. True, false or false, 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 false or false, false, and false or true, true. So for an or, if as long as at least one is true, we get true. And what we can see is that these have the same outputs for every possible combination of inputs. Therefore, those two statements are logically equivalent. So we'd say that P if and only if Q is logically equivalent to P and Q, right? Either they're both true or they're both false, which again is what we saw in this truth table and also what we saw in that definition. So that's how we go through and prove two statements are logically equivalent. We just show they have the same truth table. Okay, so for a question that I want you guys to do is I want you to show, using truth tables, that P implies Q is logically equivalent to not Q implies not P. So you might want to set this up by doing your P and then your Q. And then we know what the truth table for P implies Q looks like, so go fill that in. And then do a not Q and then a not P. And then just by comparing this to this with that implication symbol, you can figure out what not Q implies not P looks like. So I'll leave that for you guys to think about. My writing is going a little up. If you write up as you go across the page, it means you're optimistic. So I'm very optimistic on these slides. These two statements here are called De Morgan's laws. They tell us how to negate ands and ors. And what we're going to do is we're going to show that these two sides of the equivalence are equivalent to each other using this techniques of truth tables. So let's see how that's going to work. Again, I'm going to have my P and Q. I'll draw all those possible combinations of inputs. My nice pattern that I like to use. And then I'm going to break this down. So I have both a P and Q. And then we'll have a not P and Q. And then we'll have our not P, not Q, and then our not P or not Q. All right, so let's fill some of these in. So I have P and Q, so that's only going to be true when both are true. So it's true in the false first case and false otherwise. And now if I negate P and Q, I'm going to get false, true, true, true. So I'm starting with a false, true, true, true on the one side of my logical equivalence. Let's look at the other side. Got not P, so that's false, false, and then true, true. Not Q, negate that, false, true, true. And now I'm doing an or, so that's going to be true as long as either one is true. And I can see from these two columns here, these are the same. Therefore, my two statements are logically equivalent. I'll leave the other one for you guys to work on, but if you work through that, you'll also see that those two statements are logically equivalent. Let's think about why this is true. All right, what is this first one saying? It's saying that if it's not P and Q, so if it's not the case that both P and Q are true, then that's the same as saying either not P or not Q, right? Or both, because our or in math always means or both. So if it's not the case that they're both true, then either one is not true or the other one is not true. Right, so that's what De Morgan's law is saying, and that makes sense. Let's say what this one says. This says not P or Q is the same as saying not P and not Q. Right? So if it's not P or Q, it's not like the union of those, then that's the same as saying that it's not P and also not Q. Because if it was either P or Q, then it would be one of those. So I encourage you to kind of think through that and see if you can come up with some examples to help you really get that inside your mind. On this side, you'll see several different logical equivalences that we'll see a little bit used in the next couple of sections. So we've talked a little about the contrapositive. We haven't called it that, but that's a good definition to know. So if I know P implies Q is true, then I can always turn that around to not Q implies not P. And when I do that, when I negate them and switch the order, that's called the contrapositive. And so this is the contrapositive law. Now that's different than the converse. We saw that even though a statement is true, its converse is not true, but its contrapositive is true. We just looked at De Morgan's laws and talked about those. We also have this commutative law, right? It says if I have an and or an or, it doesn't actually matter which order I put the statements in. Those are going to be logically equivalent. We have these distributive laws. These are sort of interesting, right? If I'm doing P and either Q or R, then I can do P and Q or P and R. And the same thing happens if we switch the or and the and. So I encourage you to kind of keep those in mind. You'll use those a little bit on the homework. And the last ones are associative laws. And here we have to be really careful. If these are the same symbol, right, it's an and or an or, then I don't really need my parentheses. I'm going to get the same thing. If they're different symbols, that doesn't work. So this associativity only works if we have those same symbols. Okay, so in class we're going to talk about this. I want you to show that the statement P implies Q is equivalent to the statement not P or Q. So go ahead, work out the truth tables for those. If you want to put them in the slide in advance, you can, and we'll talk about that in class. And the last thing here, I've got one more discussion question. Let's consider this sort of thing related to associativity. So here I have P or Q and R. And you can interpret that either as P or Q and then and R after that, or P or Q and R. So I want you to use truth tables to determine if these two statements are the same as each other.